Hi. There we go. Okay. Hello. Yeah, Grokking, modular addition, and representation theory. I'm going to talk about a couple papers. I'm going to talk about Neil Nander's original paper and then my follow-up paper mostly. Hands up if you're like super familiar with Neil's original paper and if I should skip that stuff. Okay, I will not skip it. Most people do not know it. Okay. So this format is heavily cribbed from Jesse's format. I like the theme. It's nice. Thank you, Jesse. So this talk, Grokking. Most people know what Grokking is, so I will probably skip over this quite quickly. Representation theory. I expect some of you will probably know what representation theory is, but I'll give a brief definition of what a representation is. Universality in the mechanistic interpretability sense, and then part 4, which is new in this talk. So people who have heard it before will not have heard this bit, phase transitions. Okay, Grokking. I'm very proud of this figure. I made this for my ICML poster, and I blew it up massive because I thought this might get people to come to my poster. It's for XKCD style. It's kind of cool. Yeah, this is real data. Yeah, this is modular addition. You can visit map.lib flag. You just use with XKCD, and it makes it look like that. Yeah. Yeah. Yeah, it's pretty awesome. I will not explain what Grokking is because I will assume everyone knows what Grokking is. This is Grokking. Okay. This is not a log X scale. This is a legit scale, but we do use weight decay, which is a more aggressive regularizer than the original Grokking paper. Okay, there are a number of papers on Grokking. This is the first one, Power et al. They sort of introduce Grokking. I won't talk about this one too much. I'll talk about this paper quite a bit. This is Neil's paper on Grokking. So this is where he trains small transformer networks to do modular addition, reverse engineers them, and then creates these progress measures, which he uses to explain why these models undergo Grokking. I'll also talk about my paper, this follow-up, where we generalize the algorithm, which Neil discovers for modular addition. We realize that modular addition is just composition of a cyclic group, and the algorithm that he finds can be generalized via representation theory to any group, and then we reverse engineer how this group composition task is done in general. So I'll talk about that as well. Focus, yeah, cool. There have been a number of other papers on Grokking. The ML community is obsessed. There are many of them. Quite a few authors of these Grokking papers have been around. So a couple by Eric, who was here yesterday, Laro. Jesse is also on this paper, so Jesse as well. Cool. Modular addition circuits, yeah. So this is the first thing Neil does in his paper. He figures out how small transformer networks do modular addition. Who is super familiar with this circuit? Not many of you. So okay, I'll explain what's going on here. So okay, the task is I give you inputs A and B, and I want you to do A plus B mod 113 and spit it out as a token. So notably, these are not real inputs. These are like one-hot embedded inputs, i.e. each number gets its own dimension in embedding space. So this is like substantially easier than like modular addition in general, if you just gave it real numbers, which is important, and most people don't realize this when they first see the Grokking stuff. And in some sense, this algorithm is more natural if you think about it in this frame. So what is the algorithm? It's pretty weird. You first embed the inputs as Fourier transforms of the inputs according to some frequency omega. You then, so this can be thought of as like rotating the inputs around the unit circle, where how much you rotate by depends on like what your modular addition thing is, what your P is, what your modulo is. Then in the middle bits of the network, so that happens in the embedding. This is the architecture. It's a one-layer transformer. Yeah, so that happens in the embedding. And then in this bit in the like transformer block, this composition happens. So what's going on here? You're computing, in essence, you're combining information from the two tokens. So in one token you have A, in the other token you have B. You are combining these into information about the sign of the composition of A and B and the cause of the composition of A and B. And you do these via these formulae, just cause and sign addition formulae. So in pictures, this is like adding up these two rotations. So you have this, and you can look at the residual stream at this point, and you can find the presence of terms which look like this by doing a Fourier transform and looking in the Fourier basis. Then what happens in the unembed does quite a lot of computation. What the unembed says is, okay, I know the correct answer. I want to calculate probabilities for all the outputs C, and I want to maximize this if A plus B is equal to C. If A plus B is equal to C, then cos of A plus B minus C is 0. Cos of A plus B minus C is maximized, and this frequency omega makes sure that you're only in the domain 0 to 2 pi. So these are your output these are your output logits. The logit which is maximal will be the logit such that A plus B is equal to C, and that gives you the correct answer. And this is entirely linear in terms of if you have this term and if you have this term and you memorize this term and this term in your unembedding matrix, you can calculate this thing. Does this make sense? Question? Yes, this is reverse engineered from network weights and activations. Yes, yeah. Sure, yeah. Yeah. So this is like the standard anthropic transformer diagram. How we think about this is we input tokens, which are like the numbers 1 through 113, effectively. And you input 2 of these. These get embedded into yeah, it doesn't matter that much. Yeah, it's not important. Yeah, you embed these into a vector space, and this is like you think about this thing as the residual stream, which is like the backbone of the transformer. So everything reads from the residual stream. So this is like reading from a residual stream, doing computation, and then putting information back in. H's are the attention heads. So this is the attention layer. That's the MLP layer. So this whole thing is one transformer block. Yeah, so you have 2 skip connections per transformer block. Then the MLP does some more processing. I'm not I think in this paper, the MLP is like basically not that important. Yes, I think most of this happens in the attention heads. But don't quote me on that. Yes, yeah. It turns out this architecture is kind of overkill to do this task, and we end up simplifying it a little bit. We remove attention and we do like a less big brain thing and just like find some other way to combine the inputs from the 2 tokens in our follow-up work, and it can basically learn the same algorithm. Actually, I think the MLP is important. Ignore that comment. Yeah. So then you at this point you have terms like this in the residual stream, and then this unembed thing is converting you back to tokens. So you get like 1 logit per possible output token C. So you should think about logit C as like a vector of logits. Lara?
Is the way to think about this that so you're in the first layer you get a token A, and then the activate or like the embedding vector is
the embedding
direction along the unit circle something like because it's not sign of this thing and cause of this thing. It's are like not actually doing the activations, right? Represented as a vector somehow.
I'll get back to you about that. I think what we normally do is we like plot activations over like all of the inputs. And if you do this, you can see very clearly these things are periodic, and that's what makes you think about doing these Fourier transforms. Yeah.
Firstly, the unembedding is about time embedding.
Correct.
And you're saying that this person that you see time is memorized in the unembedding rather than the NLP?
Yeah, so like this thing, anything that depends on C has to be in the unembedding, right? Because C is your output. And anything that has an A plus B in it has to come from prior computation. Does that make sense? Yeah, so effectively your unembedding is converting things that look like this into this cos thing.
Yes. I don't see why the NLP could learn the first time that
Because C is the index of the output.
C logic.
Yeah. Yeah.
Is W 25113 or do I look at the there's like a few different?
Yeah. So yeah, this is kind of important. This is like one circuit. This is one complete end-to-end circuit. Omega is like is that an omega? That's a W, right? W is a parameter, and the model can learn this parameter. And it turns out that it always has to be a multiple of 2 pi over 113, or upside down, one of those. It has to be a multiple of these, and what multiple it learns, there's like 113, 112, I guess, possible multiples it can learn. And it always learns a sparse subset of these. And they're all kind of equivalent. They all correspond to like different frequencies that you could do the Fourier transform in. And in this case, for the cyclic group, all of these are kind of equivalent because we use prime ordered modulos.
Very expensive prime search.
We didn't do non-prime because it was more complicated. It was a bit of a mess. Yeah, the Fourier transform kind of decomposes right into like 2 bits in that case. It was just harder to interpret, and Neil thought that this was just a simpler case to look at. Other questions? I don't know. Cool. Okay, yeah. After you have this understanding of what algorithm the network is implementing, you can start to understand how grokking happens. So what Neil does is he says, okay, I know what's going on here. I know what's going on in the residual stream here. According to this general algorithm. Therefore, what I can do is I can like basically do patching. I can like patch in the correct input or the wrong input here and see what happens. So if you were at my lightning talk, lightning question answering thing on Tuesday or something, I explained what was up with progress measures. Briefly, you have these 2 progress measures. You have restricted loss, which is tracking the performance of purely this algorithm, by which I mean you patch in what you would expect here. So you patch in terms like this here, and then you measure what the loss is. So that's restricted loss. And then excluded loss is sort of the opposite. Excluded loss is like purely tracking how good the memorized algorithm is. So you only test this on the training data set because you can't memorize the test data set. And what you're doing is you're like ablating anything that looks like that. You just get rid of it. And you should expect this to tank performance at the end, but not really at the start, because at the start you don't really have anything that looks like that. And this is what we see. So excluded loss seems to track memorization. So it seems to track train loss during this initial memorization phase, and then it starts going up after that as the general algorithm is learned. And restricted loss seems to track test loss better. which is what we expect. And notably, restricted loss starts going down well before grokking. So the circuit somewhat exists before the network has like undergone grokking. So yeah, grokking is not actually this sudden phase transition thing. It actually is just like the network cleaning up all of these memorization circuits, but it has learned that it starts here. Jake?
Firstly, am I looking at the wrong thing? It feels like they're going down at the same time.
So this is like kind of flat here.
Okay.
This is like slightly steeper. This is going down steeper.
Progress measure, not that goes down after 10k epochs.
Yeah, as in like the rate of change of restricted loss is higher than the rate of change of test loss in this region, which we take as evidence that the network is actually learning the algorithm during this circuit formation phase.
The other thing I was going to ask was, if the restricted loss is patching in after the MLP, is this kind of only measuring the logic part of the circuit?
Yeah, so it's like this was like somewhat of an arbitrary decision, but you can't just measure restricted loss at the logics, because you're like giving the model the correct answer, and then you're like, do you have the correct answer? And this is just not measuring anything about the model in any way, right? You're just measuring if your algorithm is a good algorithm, right? Like if you feed this algorithm in and you measure just the loss of this algorithm, you're measuring nothing about your network. You have to measure something about your network. And to measure something about your network, you have to patch it in somewhere. And where you do this is like somewhat arbitrary. You probably get different results if you do it here compared to here compared to here. But Neil decided to do it there. Yep. Yeah.
That sort of saying that those earlier parts more than
I think it's just a claim that the different parts of the network learn at different rates or something.
Could you do something like when kind of like replace a given layer with what's supposed to be into contrast to like see how other parts of this going to be.
As in you freeze a layer for the entire training run? Do you mean?
Yeah, something
Yeah,
like that. Like this is kind of like, okay, it seems to me like the assumption here is like, if all of this stuff is being learned together, then if I give it the correct input to the unembed, then I'm just checking if the unembed learned to do the correct thing.
Yeah.
Right. But now maybe I want to ask, has the MLP learned to do the correct thing? Well, I can do that by giving the correct input to the MLP.
Yeah.
And making sure that the unembed does the right thing if the MLP got it right.
Yeah, you can also do this.
And then you can like.
Yeah. Cool. I'm going to move on. I'm happy to take other questions at the end. Any other questions about progress measures in particular?
I was going to ask about excluded loss.
Yeah.
So when you calculate the excluded loss, how do you remove the, like, do you just reset this, like all the weights in the circuit to the neutral, or do you subtract?
You zero ablate ablation. You zero ablate activations. So you look at the activation. You look at what component of the activation is contributing. You basically zero ablate certain Fourier components of the activations. And you do this according to which Fourier components are relevant at the end. Yeah. Okay, part 2, rep theory. This is what a representation is. It is a homomorphism from a group to a matrix group. We only look at real representations, just maybe unprincipled, but we were like, networks only use real numbers, so let's just look at real things for now. Why we do this is because if you look at the cyclic group, all the representations look like this. They look like rotation matrices, where the theta depends on both G and your like Fourier frequency thing. So you're like, okay, this looks like kind of what the network was doing in the modular addition case, and composition on the cyclic group is modular addition. So okay, so you can like take the network, you can take the algorithm and you can generalize it in a way which I will show you how we do later. The group that we study is S5 to evaluate on the first pass whether this algorithm is implemented beyond just the cyclic group. S5 representations are harder to describe, and I will not attempt to. Here is one So one representation of S5, everyone know what S5 is? Permutation group of 5 elements. Cool. One representation of S5 is just to take permutation matrices. So for this permutation, where this notation means map 1 to 1, 2 to 4, 3 to 2, 4 to 5, 5 to 3. Just like fill in a matrix of zeros and put a 1 wherever you have this mapping. So the 1, 1 element is 1, the 2, 4 element is 1, etc. This is a representation of S5. It turns out this is not a irreducible representation, and there's this notion of the simplest representations of a group, and these are the ones that we actually study. This one can actually be reduced to a 4-dimensional thing, direct sum, a 1-dimensional thing, and that's the thing we actually study. But this is like the most intuitive thing I can show you. So yeah. Any questions about representations? Cool. Yeah, here's the general algorithm. Confusingly, we flip everything upside down. So now tokens are at the top. I don't know why I did this. I probably shouldn't have done this, but I was like, it makes more sense to do it this way. Okay, so this is basically identical to this algorithm, except we cut out the attention layer. And we just have like a 1-layer MLP, but not quite, because we have an unembedded embeds. And then we like do something a little bit strange here, where we like put the embeddings of both tokens into the same vector space just by adding them up. Yeah, we do there's like 2 ways to think about it. There's 2 ways to do it. You can either stack them up into a long vector, or you can just add them up. And these turn out to be equivalent in a way which I won't bother describing. So what we propose is, okay, instead of learning Fourier terms, sine A, cos A, sine B, cos B, you just learn the representations in some flattened sense. And this is equivalent in the case of the cyclic group, because these terms are exactly the same terms. The matrix elements are exactly the same as what Neil proposed. Then, sorry? Yes, yeah. Yeah, sorry. This is our hypothesized algorithm. We are not doing anything yet.
The only nonlinearities are relevant MLP and then softmax in the logics.
Yes, correct. Then in the MLP, we guess that something like this is happening. So it takes these terms and it does composition of matrices in some weird flattened way, and you get out this weird flattened representation of the composition in the group. This again is entirely equivalent to this thing, because these are the matrix elements of the composition. These are the matrix elements of the group element A plus B, right? Okay. And then this last step is funky. Effectively, you're computing characters of representations, and this particular character, ABC inverse, is precisely cos of A plus B minus C when you're in the cyclic group. You can see this in many ways. If you like just write out what a representation of ABC inverse is in the cyclic group, it's just representation of A plus B minus C, because inverse is just minus. And the character is just the trace of the representation. You take the trace of a rotation matrix with argument A plus B minus C, you get 2 cos A plus B minus C, which is exactly this term, modulo 2. Okay, yeah, so this is what we guess. We already find that actually, credit to Sam Marks for this algorithm, who is an MIT person. I think he works with Eric a bit now. Yeah, he proposed this, or at least he like proposed representations, and then Neil came up with this algorithm and fed me this project, and he was like, go explore. And this is what came of it. Yeah, so what we do is we test this on S5. It turns out we already know it works on CP for prime P, because that's what Neil did. So yeah, we test it on another group, and I won't go over in too much detail how this works, but basically what we do is we like look at every activation in the model and we try and understand whether it's doing the thing that we claim it's doing. And it turns out you can do this using linear probing type techniques, not probing, just like linear projection type techniques. These two pictures are kind of fun. So this one, I guess, is like tracking the development of each okay, there's like S5 has 6, 1, 2, 3, 4, 5, 6 non-trivial representations in an
Previous slide is this thing you do where you like take the maximum character. Is it a thing that the maximum character is like at the identity?
Oh yeah, there's a theorem. Yeah, there's a theorem. There's a theorem that says something like the character is maximal when you feed in the identity, and if you have a injective representation, this corresponds to the group element being the identity, and if the group element is the identity ABC.
That's the only time.
Yeah, if you have a non-injective representation, this is not the case. Yeah, and we do find some representations which have this property. So in particular, this sign representation is like a kind of parity. So this is like 1 on the alternating group and -1 on the coset. So this is not sufficient to solve a task alone, but it is really simple because you only require like 1 bit of information to learn it. And we always find that it's like learned really quickly compared to everything else, which makes sense. Yeah, so this plot is like tracking the development of all of the different representations you might find in a network, and you find that we find in this case I think 2 are learned, and then you can plot like what the logits look like, just a slice of all the logits across all the inputs, and you find that like if you just stare at these, they look very similar. So this is like the observed logits. This is like what you would predict if you only used the sign representation. So you see it's like not completely it's not enough to solve a task alone, but like you can see these 2 look kind of similar because this is a component of this. And then this is just like a mess. This is like what the logits look, the characters are like if you use the standard representation, which is the one we find is most commonly learned. Cool. Yeah, I won't go over these details too much. You can ask me at the end if you're interested. Okay, moving on. So I guess the next interesting question is like, how generic is this algorithm? We've tested it, I guess, on CP and S5, but we really want to know if it like is general, or if we just, or if it's these examples are just super cherry picked. And we do this sort of inspired by this Chris Oler type universality criteria, where universality is this hypothesis that networks don't learn sort of ad hoc arbitrary algorithms, but if you train networks on similar data, on similar tasks, that they will learn sort of convergent representations, convergent algorithms. So in this figure, what's going on is we're doing feature visualization of like early layer neurons in various vision models of like somewhat different architectures, and we find that like qualitatively they all look kind of similar. So you have these curve detector neurons, which are like detecting curves. You have these like high-low frequency detector neurons, which are detecting changes in frequency. And these seem to appear no matter what architecture you use, what initialization you use for your model. And this is something which is very important in mech-interp, because it's like if you don't have any form of universality, then insights you glean from interpreting one model will not carry over to other models. Whereas if universality is true in a strong sense, if you interpret one model, you have like somewhat understood all of the different models which are doing similar things. At least this is the claim. But so far, no one's really investigated universality in a very systematic way. You sort of have examples like this, which are like probably very cherry picked, which are like, look, pictures look similar, but there wasn't much beyond this. There's a bunch of literature on representation learning in machine learning, representation being different to mathematical representations of groups. This is like saying I have a network, I have another network. I want to compare how similar the features are in these two networks. And there's a bunch of techniques for this, but there's relatively less. Okay, firstly, you have no ground truth there. You're just comparing two different networks. And secondly, there's no analysis of like whether the circuits implementing these things are similar or not. Ground truth for what the features you expect are. Right. Yeah, but the claim is that in all this representation learning literature, there is no ground truth. You're just like comparing two things that you don't understand. Whereas in this work, what we try and do is like investigate universality somewhat systematically, because we understand what the features. Well, okay, if networks tend. Right.
If you found this algorithm present in one of them, and universality is true, then this algorithm.
Yeah, we're trying to test whether universality is true or not. And what we do is we just study more networks, more groups, more architectures, and see if we find the same algorithm or not. And we find a form of weak universality, we call it. So I won't explain what all these numbers are, but yes, yeah.
One particular algorithm. We expect every network to use exactly the same form of sorting algorithm if it does sorting.
We don't make claims about what this means in general. We talk about just what's going on in these networks. But yeah, this could be an interpretation of what strong universality is, which probably seems false. Yeah, so we interpret a bunch of different networks trained on a bunch of different groups. Could have done more, but I ran out of time. So we did cyclic, dihedral, alternating, and symmetric groups. And we basically find the same algorithm is learned with different key representations every single time. Each of these is like 6 runs. These are averaged over 6 runs. So this is like something like 100 networks. Yeah, these are various metrics that we computed.
I see 7 groups and 6 runs. The product of that seems like 42, not like 100.
Okay, and then we do some other thing later where we do 50 runs of something else. So we end up doing 100 runs in total. Yeah. Yeah, so we find this algorithm is learned in fraction of variance explained. Yeah, so we look at MLPs, we look at the original transformer architecture that Neil studied as well. Yeah. Okay, so in Neil's original work, there was this free variable of which frequency was learned. The generalization of this to our algorithm is there's a number of irreducible representations of groups, and the algorithm can learn any of these. So taking this one step further, we can ask which representations do networks learn, and generically we find strong universality does not hold, in the sense that networks tend to learn different representations every single time. So what's going on here is we're training 50 networks of different random initializations on the like S5 composition tasks. And we find that commonly we learn these 2 representations, the sine and standard ones. The sine one makes sense. We reason that this is like really simple, so networks should always learn this. And then we find like this weird tail of other representations sometimes being learned. And then we also look at the number of representations which are learned. Commonly we get 2 or 3, sometimes we get 4 or 5, and we're just very confused about why this is the case. Yep. In a single run, how many different representations are being used to solve the task? So the way we do this is we say the logits are a sum. We expect the logits to be a sum of characters across different representations. If the network uses at least some percentage of this character, then we call this representation key. I think it's like 5% or at least or something or maybe it was lower than this, something like this.
So in Grokking, for example, this would be
Different frequencies. Yeah. And yeah, Neil found this as well. He found that in the modular addition stuff, which frequencies are used varied, but this makes sense because they're like they're all kind of equivalent. But also the number of frequencies used kind of varies, which is like maybe somewhat more surprising. We're fixing the dimension of the hidden layer. We say nothing about like what size your representation can be. In particular, like okay, maybe there's like a bottleneck here, but in particular, what was I going to say? Yeah, so this was our hypothesis, right? We thought that lower dimensional representations were simpler, but this is kind of a confusing metric because the lower dimensional ones are also generally less efficient. They give you like less performance per weight norm. So the network is trying to trade off performance against weight norm, and something maybe simpler while also having like higher something maybe simpler to learn in that it has like fewer degrees of freedom, but it also might be less advantageous from a weight norm perspective. So I think the most efficient thing you can learn from a weight norm perspective is this complicated 6D representation with like 36 free parameters. But the sign one is like one free parameter, and networks tend to learn this one first. But the trend is like somewhat not clear. Yeah.
What are these representation sign standards?
Requires a lot of maths to construct these things. Yeah.
Seems like this could vary over time.
Yes.
So are these sort of fixed?
Yeah, so like we study them at the end of a training run once it's converged. If you look at this plot, top right, this is like tracking what exists over the course of training. And you can see this is non-constant. So like at this point, say, we've only learned the sign thing, and loss is correspondingly pretty bad because the sign thing can only like halve your loss in some sense. It just divides your search space in half because it restricts you to the right coset of the alternating group, but that's it. And then later in training, we learn this standard thing. And it looks like we also kind of learned this standard sign thing. And then later on, the network's like, nah, I don't want it, and then throws it away.
So go back.
Yeah. And this is just weight norm trading off against. So yeah, I think the neurons which did learn this thing just eventually turned out to be off at the end. They didn't evolve into something else. They just turned off completely.
This is one where the number of
2. Yeah. Okay.
It's strong setting up a bit of a storm. Isn't the question of does it use representation theory to compute the answer, and then like the idea that it might use a specific representation every time? Did anybody use it?
Some people did. Some people were surprised by this result. I was not. Neil was not.
There's a sense of some representation better than others.
There is some sense of this. We're not clear. It is not clear, but it was not clear from this work which ones were best. But presumably there is.
Maybe terms regularized are like really up high. And then...
Potentially, yes. But yeah, the claim that it learns to use representation theory every time is this weak universality claim. Perhaps this nomenclature is bad, but
Strong play.
yeah. Sure. Yeah. I guess like one thing we found is like after thinking about it a bit, the inductive bias of this network does lend itself very well to this algorithm because it's basically almost entirely linear, right? The only nonlinearity is in computing this product of activations. And it turns out that ReLU can do that. But this step's entirely linear. This step's entirely linear. It makes sense for the network to use linear things. The corresponding linear thing to use if you're dealing with groups is representations. It kind of makes sense.
When you say that it's
Yeah, this is like multiplication within a it's not like multiplication of reals in general. You're like learning to memorize specific pairs of A, B input and multiply those. They're like mostly 1 or 0 or -1. Yeah. I'm gonna move on. Ask me questions at the end. I want to move on to phase transitions. Juicy stuff. How much time do I have, Jesse? Okay. So my first point here, progress measures are developmental interpretability. This is at least like the first pass of what developmental interpretability should be, I think, in my mind at least. In the sense that you understand some property of your final model, and then you pass this back through training, and you see, does this property emerge suddenly or does it emerge slowly? This is what this progress measures paper did. This is what we're trying to do with like a fellow GPT or Tokipona. A bunch of things we're trying to do in this manner. Yeah, progress measures are a powerful tool. Secondly, phase transitions in training steps maybe exist. So we had this example earlier where over optimization steps, it looks like there's a really sudden phase transition here, but maybe this is just an artifact of this stupid log x scale. But we do see this to be the case in other networks. So if we track, yeah, that's a log scale. This is not. This one's not a log scale. So like some of these don't look like phase transitions. So this is a progress measure. This is something that we understand after we interpret the network. This sign thing, that looks like a phase transition to me. That looks pretty sudden. Everything else looks kind of not sudden, but maybe there are phase transitions here. Maybe Grokking itself, I haven't got a Grokking plot here, but Grokking in these networks looks pretty sudden. So this plausibly could be a phase transition or not. So I guess in this plot, test loss is like kind of going down from the very start. Like you have this initial very quick memorization phase, but after that, test loss is going down. It's going down quicker, but maybe this is not a phase transition because it's like somewhat slow. This is not a log plot. This is, you always log loss. Yeah. Okay, but also this is confusing, right? Because there's like something going on here. This looks like very discontinuous here. So maybe this bit's not a phase transition, but like that maybe this bit is. I don't know. We need to figure this out. If you look at the progress measures, things very much don't look like phase transitions, in the sense that even though you have this like sudden grok, okay, these are not the same plot. These are like different runs. Sorry, from the top right to the left. These are modular addition things. The loss plot looks very, very sudden in these in the run that corresponds to these two networks. But if you do this analysis of progress measures, everything looks really smooth beyond this initial phase. Everything's sort of evolving kind of smoothly. So maybe there's not actually any phase transitions in these Grokking networks besides this initial when do I stop memorizing phase. Need to work this out. Again, if you look at this other type of progress measure, things look kind of smooth. Here you don't even see the initial memorization phase really. Everything just like looks continuous, looks differentiable. One hypothesis for why we might not get phase transitions in these networks is this lottery ticket hypothesis, suggesting that maybe all the circuits, so Neil's interpretation of the lottery ticket hypothesis in these networks is something like maybe the networks already have all the circuits at initialization, but we also have a bunch of noise. And over the course of training, maybe what's going on is all this noise is just being killed off, and the circuit is being amplified. And these progress measure plots seem to suggest this is the case. They seem to suggest that these things start off near 0, but not quite at 0. And over the course of training, they're just evolving in amplitude. I don't know. Right. So maybe Yeah, so maybe it does start at 0. If it starts at 0, maybe there's a phase change right at the start, but maybe there's no phase changes from then onwards. From then onwards, it's completely continuous. I don't know. There's other things that you can look at in these networks to establish phase transitions. So in N is one of them. You can also vary the fraction of the. So okay, in these tasks, you have a fix. You understand it's the algorithmic tasks. You understand the entire distribution of training data, and we vary this frac train thing, which is the amount of training, the amount of all the data that you train on. And these are some plots. This is from Power et al. It's from Neil's paper, where you vary this, and you see that you go from like not generalizing to generalizing. And these all look somewhat qualitatively different. This definitely looks different to that. That maybe looks different to this. Maybe this is a phase transition. You get this in other tasks as well, in other algorithmic tasks. The proportion of the total amount of algorithmic data that you train on. So in this case, you have like a multiplication table. And how much of this do you give? Sorry, yeah, go. I think all of these are on the same number of training steps. Plausibly, we just haven't trained long enough in these two networks for grokking to occur. Maybe it happens, but it's like exponential in the number of. It's like an exponential relation, and maybe you have to go all the way over here for it to grok. I have no idea. I don't think so. I think this is like the original grokking paper. They were just trying to find the interesting stuff. I guess because this is like you can talk about this. Yeah, you can talk about this across different networks, across different tasks. Sorry.
Are we sure it's the right framework?
No, we're not sure about this. I haven't got much left. Another interesting thing you find in these networks is you find a lot of structure in if you visualize things in a sort of toy models fashion. So this left plot is from Power et al. What they do is they apply t-SNE, which I do not understand. It's probably incredibly cursed. It's way less nice than toy models. But you apply t-SNE, you get nice-ish structure. You get this ring structure for modular addition. You get this clustering thing for S5 composition. What we do is we try and replicate this and try and figure out what's going on with these. So these clusters all correspond to cosets of a particular subgroup of S5. Pretty weird. We replicate this plot. We fail to understand it. As I understand it, there's a guy on Elufa AI, on the Elufa AI Discord, who's been working on trying to understand what's going on with these cosets, and has made some progress. So there might be something out about this soon. Might be an update. But yeah, this clustering is interesting, and maybe this is actually meaningful. I'm not sure if it is, because this is t-SNE and this I believe has some randomness in it. Okay, future work. Other phase transitions you can probably extract in these networks by varying the capacity, varying the model width. I think I think maybe what happened was going on in this plot where we never learned this 6-dimensional representation is our capacity was just bottlenecking this. Maybe if you like blow up your network to be super wide, maybe you don't need 36 parameters for this thing. Maybe you need way more. Like for example, for this thing, networks tended to use, I want to say order 10, when you can do this thing in, I believe 4 neurons. Don't quote me. It's either 4 or 8. Yeah, so this is one thing you can change. Regularization strength is another thing you can change. We know this affects the time at which networks grok. Maybe it affects other things internally. In this simplification, where we throw away the attention layer, we have quite a simple network. We have embed, MLP, I'll embed. I expect the ReLU is not very crucial to getting these networks to do these tasks competently. I expect you can replace it with a TANH and it will still work. So maybe we can get analytic traction on what's going on here. The softmax isn't important. Well, it probably is important, but you can probably get away from that away as well. Yeah, I didn't think about the softmax, but yeah, you might be able to get around this. Another interesting thing that's quite simple is this parity circuit. This is the only thing in the network that I claim I have entirely reverse engineered, in the sense that we black boxed the actual operation of matrix multiplication. We thought this was too cursed to try and understand. But in the case of the sign representation, the parity circuit, this is like one-dimensional. You don't have to do any changes of basis. So we were able to completely reverse engineer how this multiplication was done. It was still quite cursed. You like use a ReLU, and you like, I think similar to what Jake was talking about a few days ago. Details in the paper. This is also very similar to what Eric did with his parity addition circuit. It's basically equivalent. I expect for networks that he trained were doing something like this. But yeah, this is a toy task which you might be able to do something with analytically. I don't expect you to be able to get a nice phase transition, really. I mean, like you have a phase transition where it like learns the thing. You'd have this spike in training, I expect, but you probably wouldn't have. You probably only have this one meaningful phase. And maybe it's not that interesting, but this is something you could study. Yeah, thank you. That's my talk.
Much questions?
I'm incompetent, so I just need to understand how you're finding the representations are being learned. Like you know what
Yep. Yep. You don't need a probe. In fact, you can just do a projection. But it's basically this. Yeah.
So in general, just like the algorithm would require you to know what sort of
Yeah, we exploit ground truth knowledge of what the representations look like quite heavily to do this. Yeah, we looked at every point we could. So we study, I guess, like, okay. This table studies the embeddings and the unembeddings. This table studies the MLP activations. This figure and this figure study the logits. Yeah. Thank you. Other questions? Yep.
So I think on progress made, comparing to the, or at least expected, measure this, right? So you're learning somehow with that. Yes, you have something to the expectation there.
Yeah.
Or progress measure.
So I guess some very simple things that don't rely at all on understanding the actual algorithm that we did try were, there's this thing called the Gini coefficient. I don't know how you say that. This is a measure of how sparse you are in the Fourier basis. I guess this relies somewhat on you understanding, but then the network is doing something in the Fourier basis. This is one thing. Another thing that's quite illuminating is this total sum of squared weights. This is interesting in the Grokking setup because we expected weight decay to be very important. And you find that in this initial memorization phase, your weight norm grows very fast. And then from there onwards, weight decay can be seen as the dominant thing in some sense. So weight decay is killing you off. And in this circuit formation phase, some weight decay is killing off some of these memorization circuits. And we see a phase change of some sense in this region. The weight norm is decreasing faster here than it is here. And this is what we call the cleanup phase because of this. And then after this, it's stable. So yeah, I guess this is an example of a progress measure. It's a very basic progress measure. but something which is telling you something meaningful, at least in this case.
Got it, got it.
5-minute break? Yeah, that's really cool.
Thank you.
You think, I mean, the example with the representation is a place where we know some sort of universality holds and is therefore